Hi everybody, this is unit 4.4, the wave behavior. So let us try to understand now what exactly is expected here. So we are going to understand about the reflection and refraction. So if you remember from your prior knowledge we have seen reflection on polished surface like mirrors, and it was about having it in same medium. Okay, but then refraction, we saw light ray traveling from one medium to another, So we are going to talk more about reflection and refraction a bit longer. We will begin with refraction first. So what exactly do we understand by Snell's law? Now Snell's law, this law particularly states that the ratio of sine of I by sine of R is a constant. Now what is sine I and sine R? So to understand that, we have to move into a medium which is like, say, air, and you have your glass. So a ray of light is coming from air and entering the glass. So we draw a normal here, and then this is the actual part, but it will bend here, right? So this is called the first one is called your incident ray. This is your incident ray, and this is your refracted ray. This angle is angle of incidence, and this is angle of refraction. Okay, we have studied this in the lower grade, grade 10 and grade 9. So the ratio of sine I and sine R, that is a constant, and that constant is given as n, and this n is known as your refractive index. Okay, refractive index. Now let us go a little more ahead. So what exactly can happen if a ray of light has to go from reverse, let us say glass to air? So this time the ray of light is going to travel all the way from your glass and then to this. So this is your R and this is your I, because this is your normal, right? If I happen to increase this angle, what probably would have happened now? See, so I can increase this angle, right? And then I can make this angle such that this ray will lie exactly on this. So I am going to have this and this. So if you look here now, your R has becomes 90. So the angle of incidence for which the angle of refraction becomes 90 degree is known as critical angle. Okay, critical angle. What does this mean now? This means that if my R becomes 90, then my I becomes C, the critical angle. critical angle. Therefore, I am going to use this formula. N is sine I by sine R, which is equal to sine C by sine 90. Now, when you write this N here, the refractive index, it is always written as from where to where. So, it is going from glass to air. This means from glass to air. Now, if this is the case, then for this equation, I can now write this as N equal to from glass to air as sine C. Therefore, if I reverse them and if I write A and G, this becomes your 1 by sine C. Okay, this part. Now, this one is also known as at times the principle of reversibility. And this says that if you go from A to G is equal to 1 by G to A. So this statement also means refractive index of glass with respect to air. Okay, so this is one part of that. Now coming to the other part. So let us say one application question let us do here, and there is another formula here. So N is equal to, for example, let us say it is coming from air to glass, then it is also given as speed of light in air by speed of light in glass. Okay, so this is called the first medium and this is called the second medium. Now, technically, the speed of light in air is 3 into 10 power 8 meter per second. And this is 2 into 10 power 8 meter per second, which means it is 1.5. Now, let us go for one higher order question. So, the higher order question, let us take something very interesting. So, we will take question: if light travels from air to water to glass. So I am going to have a situation. This is air, water, and then I have glass. So what would technically happen? Let us see now. So the ray of light would come here, normal. This is the original, so would bend little down and normal, but this is still bent down. See, the light ray would keep bending, towards normal, because it is all the time traveling from rarer to denser. So between these two, if I work between these two, then it is like A and W, which is equal to speed of light in air by speed of light in water. where S stands for speed of light. Okay, if I work between these two, then I will get W and G. So speed of light in water by speed of light in glass, right? So therefore, if I multiply A and W times W and G, I will get speed of light in air by speed of light in water times speed of light in water by speed of light in glass. So I can cancel these two, which means I will get speed of light in air by speed of light in glass. Now this part, if you see this part, don't you think this is nothing but A and G, because that is speed of light by speed of light in air by speed of light in glass. Hence, can't we write this formula as A and W times W and G is nothing but A and G? See, okay, so this is technically the Snell's law and the application of Snell's law. So let us now go to critical angle and total internal reflection. Okay, so I will begin next the critical angle. Let's a critical angle we have done now. So critical angle we have done up there. Let us do now total internal reflection. Okay, so if you do this total internal reflection, we just saw here the cases. One was the case where the light would bend, single. One was the case where the light would go on the surface, double arrow. So this was I, this was C, and if I go beyond that, so I go up to here, such that my angle of incidence becomes more than critical, then what happens? Then your ray of light starts bending down. Now this case is called your total internal reflection. Okay, so why are we studying this? The applications, there are many applications here. One of the application is mirage. We see in the desert, where we see the image of clouds on surface, which appear as water, right? So we also have seen rainbow. So if we are between sun and water drops, then what happens is, if this is the sun and if this is the water droplet, then the light from the sun would enter here, would go inside, bend inside, and then would come out. So we watch from here. So total internal reflection happens inside the bubble. Okay, this is the water drop or bubble, water drop, let us call it. Okay, so if your position is between these two, so you are between the sun and the water drop, then you can see this. Okay, this is another application of that. Now I'm going to recall something from the previous, the unit. So I'm going to do a brief recall from 4.3. So it was about wavefront. So we have seen that wavefronts are nothing but, you know, a set of lines, correct? So it can be plane wavefront, it can be circular wavefront, okay? Now how do we apply these things to your refraction? So you should also know that the direction of wavefront is called ray of light. Okay, that's a very important thing here. So if I have a surface, for example, say this is a surface, okay, and I have these as my wavefronts. So these are the wavefronts, these are the wavefront, these are the wavefront, these are the see, these are the wavefronts. So if these are wavefronts, then obviously what is the direction of the ray then here? The direction of the ray would be something like this. See? Like this. And then if this is a normal, then your ray, instead of going this way, will bend. We all know that, right? This is, so this is the refracted ray, this is the incident ray. Okay, now let's go back again to this one. How would this behave now? So this will behave something like this. It will bend, it will bend, and then bend, and then it will still bend, it will bend like this. So these are refracted wavefront. Okay, wavefront. If you see here the gap, the wavelength has decreased. The wavelength has decreased. Okay, because the wavelength is the gap between these two. So that has decreased. So this is the refraction of a wavefront. Of course it is same as the ray, because you see the diagram is almost same, so there is no problem with that. Now let us go. So we have done all this. Now we have done refraction, we have done this, we have done Snell's law, we have done the critical angle, total reflection, and all those we have finished now. So we are going to go a little more ahead now. Okay, now we are going to understand another concept here. This concept is about diffraction. So we are going to understand diffraction. You know, light bends around edges. Okay, so if you remember the wavefront, for example, you have these plane wavefronts. Okay, plane wavefront, and if you pass it through, let us say, a slit, this is a slit. Okay, so this is a slit, small slit, so has small slit, then in that case this will simply bend like a circular wavefront. Okay, so circular wave front. But if you have the same thing, and now you have again everything same, but this time you are not going to have such a small one. Okay, you are going to have something very different one now. So we are going to have a bigger portion. Now what will happen here is the straight ones will travel straight. See, they travel straight, but on the edges they bend. On the edges they bend. So on the edges they bend. On the edges. On the edges they bend. You know. So they bend here. See, they bend here, but then they don't bend here. They go straight. So there is a bending of light rays at edges. Okay. So this can be of different shapes. We can have another way also. We can have the same wavefront, but this time what we can do is we can bring, let us say, only one side. So you are just going to bring only one. So no slit, it is just one. This is an object. Now how will your light bend here now? So it is going to bend only in the edges. Here it will go straight. You see, it will go, sorry, give me a second. Yeah. So here it will go straight. Okay. Only thing is it will try to bend from here. So you have to bend here, then go straight. Bends here, then go straight. Bends here, then go straight. Okay. This is how it moves around your edges, the objects that you keep. Alright. So I have shown you few of the patterns. So it can also be something like this, where you can even have a particular object which is at the center of this one. So again, this will go straight, right? But this will go straight, but there will be a bending here, you see. So it will bend, then go straight. It will bend, then go straight. It will bend, then go straight. Same thing here. It will bend, then go straight. It will bend, then go straight. Bend. So it's like, you know, it will bend here actually. That's the problem. So it will bend, then it will go straight. So this is how you have to judge the diagrams. Alright. Now, coming to the other side of it. So if I take a particular slit, so single slit experiment, single slit experiment. Now this was done using a single slit, and then the light from this, you know, so this was a source which had, let us say, all this like this, and then the light was bending. So light was bending, okay, and there was lot of interference having here. So there is lot of interference having lot of interference, because light are bending, so they will interfere here. So there will be again here one, here one. So this will also be there, that will also be there, and then it will have a lot of interference. So this pattern, this interference nature causes the production of max and minima fringes. Okay. So when this experiment is performed, something like this, and then this is your screen, okay, and then we say, okay, the ray of light has bent, and then the ray of light has bent, and this is ray 1 and this is ray 2, and this is the central bright, always, okay, always, and let's say we just draw this also, and we take this as something like say B. And if I have to draw here a little bit more, if I draw here like this, and if I draw here like this, I can take theta, and this is 90. I will call this x, this much. So what is x? X is technically the path difference between the ray 1 and ray 2. Okay, ray 2. Now there are certain things you should know here. So sine theta is equal to x by b. So x is equal to b sine theta. Because it is a path difference, for minima which is dark, it is taken as n lambda. Therefore, for diffraction, therefore this formula becomes now as your b sine theta equal to n lambda. So b is what? B is your slit width, the distance from here to here. What is this? This is the wavelength. This is the number of the fringe that you are watching. Fringe. Okay. And this is the angular separation. So angle. This tells how much the ray has bent. The light ray bends. This tells that. Now if for example, again let's go back here. So if theta is very small, then what happens? See, if theta is very small, then sine theta is equal to theta. This is why, because it's almost like sine 0 is equal to 0. No, that is taken like that. So sine theta is theta. Therefore, in that case, we write b theta is equal to n lambda. Okay. So sometimes you might have to use this also. So for second minima, we write b theta is equal to 2 lambda. That is how we write. Okay. Now this is about your single slit. The single slit output also has a pattern. Okay. So there is a pattern for single slit now. Single slit pattern. The graph of this single slit will appear something like this. So this is the central bright. Okay. So it's going to appear so this side you are having up intensity. Okay, and this side is your distance. So we can judge the wavelength actually. Okay, so this is like your bright. So this is your central bright. So this is this position. I'll take another color because it will confuse. So this position is your central bright. Then this is your first minima. This is your first maxima. Okay, that's how it goes. This is your second minima. This is your second maxima. That is how it moves. So you must know that this position from here, I'll take another color because it will confuse us, so I'll take another color. So from here to here is lambda by 2. This is very important for you. because sometimes you might have to judge from the graphs. So graphs can be used to determine this value. Okay, so this is a basically single slit diffraction, the pattern that you see there. Okay, now let us say we see some analyzing questions. We just saw that B sin theta is equal to n lambda. So if we perform the experiment in air and then in water, what happens? Now we very well know that speed in air is greater than speed in water. So speed is what now? We know V is equal to F lambda. We know V is equal to F lambda. So which also means lambda in air is greater than lambda in water. Frequency does not change. It is constant, does not change. Okay. Therefore, if lambda, you see, one more thing you have to observe here in this formula is your B is proportional to lambda. Sorry, your sin theta is proportional to lambda. I'll just erase that part because it's important. So your sin theta is proportional to lambda. So which means sin theta in air will become greater than sin theta in water. So pattern will expand. So theta tells you the bending nature or the expansion of fringes. Okay, so this is how you have to learn how to judge these technically. So these are diffraction we did single slit, and we have seen around objects also. So this is how you have to work now on this concept. Let's go to the next concept also. Next one that we are going to deal now is the interference pattern. Now question is, what exactly is this interference now? Okay, so two waves superimpose on each other. So when they superimpose on each other, the energy or the amplitude or the oscillations or the vibrations may increase or decrease. For example, if I have a wave which technically has amplitude of 4 centimeter, and if I have another wave which is having 2 centimeter, then it becomes your 6 centimeter amplitude. Okay, displacement and time. Now same thing I can also show if this is 4 centimeter and if this is 2 centimeter, then this will become 2 centimeter. So the addition or subtraction of amplitude can be done from a graph. So if you are given a question, you have to look how many boxes are going up, how many boxes are going says down, how much should I subtract, and what will it become. That's how you have to judge. Okay. Now these interference patterns actually show two things. One is your constructive interference, which is also known as maxima, which also means the pattern will appear more bright. Other one is called destructive, which means it is minima and will appear as dark. Okay. So if I use light, if we use light of same amplitude, then during destructive interference, it will become completely dark. Okay, completely dark. Now so whenever you are having interference, you will always get this. So there are conditions here now. The condition for interference, is that both source have to be in zero phase difference or constant phase difference. Part difference must also be constant. Okay. It is always good to have a monochromatic source. That means single wavelength. Okay. Example, sodium vapor. Why? Because if we use white light, for some reason, if white light is used, then we will get colored fringes. Okay. Now coming to mathematical part of that. So the diagram, if I have to draw, I will have single source S1, I will have two slits, and then I am going to have the wavefronts going from this entering into this, and then I will have here separately I will have the circular fringes here, see, and I will have on the other hand here also circular. So you can see here now that there is a superposition between both. There is a superposition. And you will get both patterns. We get both constructive and destructive. So if I have to apply again maths here, then I have the two slits here. They are like S1 and S2, just like it is created here, S1 and S2. And then the overlapping happens, and then I get them on a screen. This is a screen. From here to here is a D. This is the distance between slit and screen. So it is distance between slit and screen. This is the center point, if you have observed, okay, given as y, the distance of a fringe from center. All right. Now this has a formula. That formula we need to apply. The formula which it applies here is given as S is equal to lambda d by d. Okay, we need here. Now what is what now? Your S here is known as fringe width. Then what is fringe width now? So fringe width will be your pattern, because your fringe is going to have bright, then it will have dark. So this is your dark, right? And then you will get bright, again you will get a dark. So this is how the pattern will come for you. So this is how the pattern will come for you. So this is like a central bright, then comes your first dark or minima, whichever you want to call. Okay, this comes your first bright or maxima. Okay, so the distance between any two bright is called your fringe width. Actually, fringe width. It can also be between two darks. Fringe width. That is called fringe width. And the pattern will also come something like this in this case. The pattern will be straight. Okay, that's a central bright. You remember we wrote last time up also. So we wrote like this. And then it will come here, the dark. Sorry. So it is the dark, and then you get again bright. That's how it comes. Okay. So same intensity in this case. Now let us go back to again understanding of that. So lambda is wavelength as usual, like up. D already I told you distance. This is this, and this is the distance between two slits, right? So some simple logic questions are like, one, if lambda decreases, like say lambda of blue is less than lambda of red, right? Decreases. Then what happens? Your S is proportional to lambda. Hence, the fringe width will decrease. Fringe width decreases. So, the pattern will compress. Right? What happens if D decreases? Your S is inversely proportional to D. Hence, the fringe width will increase. So pattern will expand. Pattern will expand. Okay. So this is about your double slit. So we have done that and the part difference. Now coming to this energy concept, note that the energy is directly proportional to square of amplitude. Okay, so E is directly proportional to A square. So sometimes questions may come like, say example, if energy is doubled. Now from where this energy comes is E is equal to HR or E is equal to SC by lambda, of course. But if it is doubled at all, then what happens? If energy is doubled, then it will become E by 2E equal to A square by A dash square. So E cut. So it will become A by A dash is equal to 1 by root 2. Therefore, it means your A dash will be root 2 times A. Okay, so this is about your double slit interface. You don't have much more than this in this, because this is in the core part. It is not in higher physics, higher level physics. So this is enough here. Now coming to the standing waves, you see. So what we saw up were traveling waves. So which means energy will be transferred from one point to another. Okay. Now what you are seeing, standing waves, in these the energy is conserved. Okay, but question is, how is it formed? That is the first question. How is it formed? So let's say I have a string. This is a string and it is fixed here. Okay, I am going to generate a pulse here. So the pulse will travel. When it hits here, it will reflect back. See? So the reflected and the incident, they appear in form of loops. Okay, every loop has maximum amplitude or vibration position and a minimum vibration position. Okay, so if we see a loop is formed here like this and then like this, this position is called your antinode, and these positions here and here, these are called your nodes. Okay, so there are three things here: loop formation, maximum, minimum, and then the node and antinode. So these are very important thing for us. Okay, now coming to the boundary conditions in sound, what happens is standing waves in pipes. Okay, so let us see this now. So we are going to just understand. So I am going to divide into three parts here. Okay, I am going to discuss the whole thing. One will be both side open, both side closed, and one side open. This is how we are going to discuss this whole thing. So let us begin. Both side open means it will be something like this, and the pattern will be like this. Why? Because only at only at antinode, we hear sound. Okay, but from here to here, let us say the length is L. This is length of pipe. Okay, then your L here is lambda by 2, because each of this is lambda by 4 and this is also lambda by 4. Correct? Why is it so? That also is very simple here. So if you have to understand that, you have to just remember this part. From here to here it was lambda, right? From here to here was lambda by 2. From here to here is lambda by 4. Okay, that is why it is that. So this first one that you are seeing here is also called your fundamental situation. Then comes your second overtone. Fundamental is sometimes also called as your first overtone. Okay, there are so many names also here. This is the second overtone. So this one is going to have something like this, right? So how many lambda by 2s are there now? There are 2 lambda by 2, see, equal to L. So I can write this as your lambda as just L, and here I can write your lambda as 2L. This is important for us. Okay, this is important for us. After this, when I do the third harmonic, it is also called sometimes harmonic. So many names are there here. Harmonic. So if I have to do the next one, then I think I have to do, see, this is how I have to go. I think I have drawn more. 2. I don't need so many, because from here I don't need. 1 minute. So yeah, this is correct. Okay, so this is third. So now how many are there here? Lambda by 2. We have 3 lambda by 2 L. So which means my lambda becomes 2L by 3. Now if I go up and if I bring down all of them, I will see that first one was 2L, my lambda, then it was L, then it was 2L by 3, which means I can write 2L by 1, I can write this 2L by 2, and then so on. Okay, this is how we write. And then the speed of this wave will be V is equal to F lambda, where F is the frequency. Now coming to the next one. So if we talk of the next one, both sides closed, then it is exactly same as that. So this is your fundamental, this is your first harmonic, okay, and this is your lambda by 2 equal to L, so lambda is equal to 2L. So you see exactly same. Then the next will be like this. So your lambda will be equal to L. This is the second. Third will be so how many lambda by 2's are there here? Here there are 3 lambda by 2's, you see. So it's like just 3 lambda by 2 equal to L. So it will be lambda equal to 2L by 3. So it is same as both side open condition. Okay. Now coming to this one side open condition. Let us see this one. So one side open condition is going to be this is the length. It's going to be something like this. Okay. So this is your fundamental. So which means clearly that this is nothing but lambda by 4, which is equal to L. So lambda is 4L. See. Then comes your second one. So this way. Now how many lambda by 4's are there? Again, if you see here, you get 3 lambda by 4, that is L. So lambda is 4L by 3. So if I do the next one, I will get here see. So how many are there now? Lambda by 4, 1, you have to divide, you see. So you will get 5 lambda by 4. I think 1, 2, 3, 4, 5, correct. 5 lambda by 4, that is L. So lambda will be 4L by 5. Now you can generalize again like we did up. So your lambda can be now written as 4L by 1, 4L by 3, 4L by 5. So you see a trend here. Okay, and again V is equal to F lambda. So these are your boundary conditions here, and this is how these things actually technically work. So now let's say for example, I need a musical instrument. Okay, a musical instrument, and it has a frequency of say 30 Hertz. So which is better, both side open or one side open? So if I do this in the both the side, okay, so let us say for fundamental, I'm going to work on fundamental, then one of them here will have lambda as 2L, whereas here the lambda will be equal to your 4L, right? So your length will be here lambda by 2, your length will be here lambda by 4. Now speed of sound will be same 334. Here also speed of sound will be and V is equal to F lambda. Here also V is equal to F lambda. So 334 is equal to 30 is equal to lambda, which is 2L. Here also V is equal to 334 is equal to 30 to lambda, which is 4L. So I will divide both of them. Let us say we give them name something like we give them L1 and we give them L2. So L1, L2, like that we will name. Okay, L1 and L2. So if I divide both, then I will get see. So what does it show? It shows L1 should be 2 times of L2, which means if I use both side open length has to be double of one side open, isn't it? So which is better than? Obviously one side open is better. One side open is better. Okay, so this is how you work with some of the reasoning types of questions here. Okay, and so we did nature of this, we did boundary condition, nodes, antinodes, and you have seen all of these things, the applications you have seen. So you know, sometimes there might be other questions like the fifth harmonic of both side open in a pipe of length 0.5 meter occurs. Find frequency. So if you have to find the frequency, for example, so you know 1 2 3 4 5, so the fifth will be here, if you see 2L by 5, that will be your lambda, right? The length is given to you, so you know that 2 into 0.5 by 5 is equal to lambda, which means 0.1, so lambda is 0.2 meter. You got it. Now it becomes very easy. The speed of sound will be given to you, which is 334 meter per second. Therefore the frequency will be 334 by 0.2. So it's like 3340 by 2. So 2 1s are 2, and then 2 6s are 12, 2 7s are 1670 hertz. Just an example. So this is how you should know to apply this, under what circumstances you're going to apply them. Okay, so I think that should be fine now with this 4.4 4.5. So all the best.